two-way, the delicate art of paper folding is playing a crucial role in designing robotic artificial muscles that are startlingly strong. The design uses a SO/FT material and could be safer around humans. The demonstration of strength of the artificial muscle. Shiguang Li, Proceedings of the National Academy of Sciences. Hide caption. Toggle caption. Shiguang Li, Proceedings of the National Academy of Sciences. The demonstration of strength of the artificial muscle. Shiguang Li, Proceedings of the National Academy of Sciences. The delicate art of paper folding is playing a crucial role in designing robotic artificial muscles that are startlingly strong. In fact, the researchers say they can lift objects 1,000 times their own weight. The researchers say the muscles are soft, so they're safer compared to traditional metal robots in environments where they would interact with humans or delicate objects, and they can be made out of extremely low-cost materials such as plastic bags and cardstock. Their findings were published this week in Proceedings of the National Academy of Sciences. It was surprising that they were so strong. I was surprised. Based upon the simplicity of this architecture, it's very simple. Robert Wood, a Harvard professor of engineering and applied sciences, tells the two-way. I still remember the first demo we saw. Of the system lifting a tire, and it was like, whoa, we've got to model this, adds Daniela Rust, director of MIT's Computer Science and Artificial Intelligence Laboratory. The artificial muscles work by encasing in a plastic skin, a folded origami-like skeleton, capable of expanding and contracting. The device expands as water or air is pushed into it, and contracts as the water or air is pumped out. Russ explains how this works. The fluid medium fills the entire space between the skeleton and the skin, and in the initial stage the pressure of the internal and external fluids are equal. But as the volume of the internal fluid is changed, a new equilibrium is achieved. And this is due to the pressure difference between the internal and external fluids that induces tension in the flexible skin, and the tension acts on the skeleton and in turn drives the transformation that is defined by the geometric structure of the skeleton. So if the skeleton compresses as a brick shape, that is the transformation you will achieve. Quote, the researchers say the way that the origami skeleton is folded determines the motion that the artificial muscles will make as they expand or contract. They can be programmed, or folded, to move along multiple axes and to bend and rotate. This is a snake-like robotic arm with a flower-like gripper driven by a single vacuum source. Shiguang Li, Proceedings of the National Academy of Sciences. Hide caption. Toggle caption. Shiguang Li, Proceedings of the National Academy of Sciences. This is a snake-like robotic arm with a flower-like gripper driven by a single vacuum source. Shiguang Li, Proceedings of the National Academy of Sciences. Because it is able to lift heavy payloads, the design, Wood says, overcomes a core paradox of the field of soft robotics. You're typically giving up strength because you're using soft materials. The devices are so strong, Russ says, because their design amplifies force much like a pulley or a lever does. As the origami structure inside contracts, and the outer plastic skin pulls in, it converts the fluid pressure to a large tension force on the skin. Based on their models, she says the researchers believe a 1 kilogram artificial muscle could lift 1,000 kilograms. Wood adds that he sees these models working well in environments like homes or hospitals where they might interact with humans. They're straight wrong, so we can envision things that have standalone robotic arms that can manipulate large heavy objects yet be safe to operate around, he says. Other applications could be wearable robots or robots used in surgery, things that have to be delicate in order to not harm an operator or user, yet strong enough to lift heavy loads, Wood says. Russ adds that she envisions these artificial muscles helping people who use wheelchairs to stand. We could really bring soft, strong